first thing I'll talk about is maybe the quiz. So for this quiz, again, if we've got a loop that goes from 0 to log n, and we're I guess just adding a bunch we're adding for log n times, we're adding a value, I guess, to a list using that add method from, I guess, the most recent lecture videos. What is the total runtime going to be here? So I'm seeing log n, but didn't we say that the add method was O of n? So wouldn't this be n times log n? Why would it just be log n? Yeah, so again, why this list implementation here was big O of n was because we had to do this shift of all the elements. So again, from that position to the end of the list, we had to shuffle all the elements down. And if we look at this, we're inserting into index 0 when there's no items, and then I is going to go to 1, we're going to put into index 1. Then I is going to go to 2, and we're going to put into index 2. So really what we're doing is we're kind of doing the equivalent of just adding to the back, which we've seen with our stacks and queues. If we're adding to the end of a list and we don't need to shuffle, we can do that in constant time. Yeah. So the trick here was that although this is an O of n operation at the worst case, we were actually doing it in the best case, so we never actually had to do any shuffling. So this was kind of a curveball trick question where sometimes we need to think about how we're actually using the methods. And if we can guarantee we're never going to do any shuffling, then it's not going to be big O of n. Does that make sense? Okay. I guess the other thing I wanted to talk about really quickly was, so today I think I am going to do a little bit of slides with you in the lecture. I try to avoid lecture slides just because I feel like they can be done in videos better, but I spent way more hours than I expected to doing the slides for the Q stuff. Again, doing all these animations just took me so long in PowerPoint, just because it's sometimes a fairly slow process for me. So again, but I did want to just revisit this. So I talked about these 3 different implementations using a count variable, making the queue full when size is equal to n-1, and making our front and back indexes go to -1 when it's empty. So I guess because that was kind of a solution to what we were working with right till the end of yesterday's lecture, I wanted to ask if there's any questions on those lecture videos or on these three different solutions that we have for a circular array-based queue. Okay. So method 3 the idea with method 3 is that my mouse, make room for my tablet really quick. The idea for method 3 is that when we've got an array, and it doesn't have to be 5 elements, but it can be whatever. And if we NQ 3, what's going to happen is originally we've got our indexes. Oh, whoops. No. And I'm going to write index -1 here. Because F and B both start at index 1. And then the idea here is that when we add our first item here, when it's empty, so again, when F and B start off at -1, what we're going to do is we're going to set them both to 0. So the front's going to be, and the back's going to be both 0. And then we put the object here, and then we move B forward 1. This isn't going to work. It's a nice idea, but so we can just have a smaller array here. So again, F and B both start at -1. When we NQ, we're going to first put them to 0. So they're both going to move up 1 to 0. Then we say put the object 3 into this spot and then make B go up 1 again. So B is going to now move to here. And then after that, all their NQs are the same thing. If we wanted to NQ another item, again, we're just going to say put that item into the index where B is, which is a 5 here. Then make B move forward 1. And then, so then if we start dequeuing, all that's going to do is say grab this item and then move F forward 1. So we're going to remove the 3, return the 3, and then move F forward one spot. Again, that's just kind of this stuff right here. Then if we dequeue again, F moves forward again. And again, so we've kind of now removed both of these items. And now that we've moved forward again, if we move forward and F equals B here, like they do now, then we're just going to set both these to -1. So we're saying, okay, I now know that I've removed all the elements from my queue. So I'm just going to set these back to -1 because there's no elements in my queue anymore. And then we'll just start inserting from the front again. Does that make sense? And then, and I guess, so, so it's only ever going to be full when they're equal. So again, if we hadn't done those last 2 dequeues, if I reverse back a bit, there, and I did one more NQ instead, that would put a 1 into this spot, and B would go forward 1 spot. So again, maybe this will answer the next question. Why are we doing mod n? So again, B is going to go +1. So B is currently 2. 2 plus 1 is 3. But now, in this case, n, the size of the array, is also 3. So if we do 3 mod 3, that's going to be 3 divided by 3. What's the remainder when we do 3 divided by 3? That's going to be 0. So that's actually just going to wrap B around and make it go back to index 0. And we see that, so when they're full, it's when both of these indexes are the same. So this just allows us to differentiate between when it's empty and when it's full, because when it's full, the index will be the same. When it's empty, if we ever DQ and move F up so that it reaches B, that means it's empty, so we're going to set them back to -1. Does that answer both your questions, Leo and Min Shang? Cool. Cool. Okay, so the next thing is what I'd like to do is, as I said, I'm going to go over some new lecture slides, and I think they're going to go by quite quickly because a lot of it is linked lists. But at this point, the textbook brings up another notion, another way of thinking about linked lists, and they argue that if we think about linked lists from a slightly different perspective, they can be much faster than arrays. So I'm going to talk about that a little bit, and then we'll kind of take a step back again and think about when we want to use one, when we want to use the other, and then we're actually going to do some Java coding just to get us into Java a little bit. So let me get to. So I believe this was all in the lecture videos to here. Yeah, to here. See, I didn't have time. I spent most of the day just working on PowerPoint animations. I didn't have time to record more videos. Otherwise, I would have put this as one of the pre-lecture videos. I like to do that more, but again, it was getting pretty late, so I wanted to get the quiz out. So I think all of us are familiar with a linked list from our prerequisite course. And again, it's just a structure composed of these nodes, where a node again usually holds the piece of information we want to store at that position in the list, and a pointer to the next element in the list. Depending on the type of linked list implementation, it might also store a reference to the previous element as well. So in Java, again, we're going, and we haven't seen a lot of Java yet, but we have seen those introductory videos. We're going to make a class called node, and we're going to see that it's got, if I was working with an integer list, each data element would be of type int, and it would also hold a reference to the next node in the linked list. So again, if we made a node A, we'd could call a constructor and say, okay, let's set its data value to 7 and its next is just pointing to nothing. I can make a second node, and now we've got two separate nodes. They're not linked in any way. And again, the way we link them is by setting the next pointer from one node to point to the next one. So I could say A's next now points to B, and that's going to essentially make it so we can go from A and we can go next and visit B. So we've now got a linked list of 7 being at the front of the list, and following 7 is the node with data value 3. So I think at this point, this is probably pretty review. Again, each node has a data value, which is an integer, and a pointer to the next node. Again, with linked lists, we always typically keep a reference to the head of the list, which is the front item, because from there, we can visit all the other elements in the list. So again, if we say let's start at the head of the list and keep looping as long as cur is not null, we can print out the data at cur and then make cur go to its next. So it's going to print out 3, then go to 5, then go to 6, then go to 7, then go to 9. And once it prints out 9, when it says cur is now going to cur's next, it'll go and it'll point to null. So we'll break out of the loop and stop printing out the values in the list. This is often done with a while loop as well, but again, we can see that it's the exact same. We're starting in a current node at head. We're looping our loop variable as well. Cur is not equal to null. We're printing out the data element, and then we're setting cur to next. So again, these are equivalent. We're going to start at the first node on the list, visit all the items, printing out their data value, and stop once we reach null. So I'm assuming this is review at this point, but are there any questions so far, or is this all pretty much what you've done before? Yeah, cool. Okay, so again, I'll move through maybe the next bunch of slides quite quickly then. So again, if we wanted to insert a node 20, and again, let's say this is an ordered list, we first want to determine where I'm going to insert it. So again, we'd have to iterate from the head to that position because we want to insert it between 19 and 20. And then we just have to update the pointers appropriately. So again, I want to say set ends next to be currents next, so the 20 points to 22. And then I can say the 19 points down to the 20. So fairly simple in terms of when we want to insert something within the list. I guess we have to get to that point, and then once we get there, it's just updating the pointers. There isn't any shuffling of any elements afterwards like there is in an array. I will say that the order of operations is really important. So this is what we did in the previous slide. And I'll just show off really quickly. If we just flip these two operations here. So if I said, let's first make currents next point down to n, and then make ends next to currents next, ends next will just point to itself. So we'd lose any reference to that node 22. So again, the implementation of a lot of these operations is quite simple, but it can be quite you can make a really tiny mistake in the sense that you're just flipping the order of two operations, and that can end up with huge errors in your code. So I just wanted to highlight this really quickly and just have it on the slides for you for review. And removal is the same thing. We want to locate the element preceding the node we want to remove. If we want to remove 19, and then just update the pointers so the deleted node is skipped. So all I want to say is currents next is now currents next. And for those of you that did 116, again, now that there's nothing pointing to node 19, Java's garbage collection will delete any objects that nothing points to. So for those of you that did this in C++, or maybe even C, you would have probably had to free the memory for that node object, but you don't have to in Java. The garbage collector will do that for you. And again, so what we saw with stacks and queues, and again, if we were to implement a stack or a queue with a linked list, we see that adding to one side of a list is really easy, at least the front at this point, where I can make a new node, I can set its next to be equal to head, and then make head point down to that new node. So again, quite quick and easy. At this point, if we're working with a single linked list with just a head pointer, again, if we want to add something at the back of the list, we'd have to again iterate through all n elements with our cur to get to the last element, and then from there update the pointers appropriately. So make its next now point to that new node we just created. So obviously this isn't great, and that's why that's the motivation behind having both a head and a tail pointer, because a tail pointer allows us to really quickly add things to both. We can already add things really quickly and easily to the front. It makes us able to add things at the back side of the list as well quite easily. So again, the problem here with just a head pointer is that we'd have to start at the head and loop through all the different elements in the list. So again, the idea of a tail reference is, again, we've got something pointing to the first element, something pointing to the last element, and then again, adding something to the back is as simple as just setting tails next to be equal to that new node that we've added. Mm-hmm. Any questions about this? Okay, I know I am moving quite fast. Okay. Yeah, and then make tail point to that last element we've added. Yeah, good catch. Okay, so quick summary of this kind of quick 5-minute presentation I made. Again, it allows us quick insertion and removal without the need to reshuffle other items. Again, this allows us to add items and remove items in the front and back in constant time. But accessing the middle element still requires a traversal to get to that location where the insertion or removal takes place. So that is still going to be O of n. So the next thing I'm going to do is talk about a few variations of this. So I think probably something else that is likely review for you is a doubly linked list. Again, the main difference is that each node, again, now, before I said it sometimes has a pointer to the previous element, this is when I'm saying that this implementation does have both a next and a prev pointer. So again, we think of our nodes as having kind of something going to the node previous and the node next. So 7 goes next to, or set node A, which has data value 7, goes next to B, and B can go previous, follow its previous pointer back to node A at 7. So again, insertion is very similar. Move to the place we want to insert. And we just have a few more pointers to update. So now we can say ends next is going to be curs next. Ends prev is going to be cur. Curs next prev is going to be n. And then curs next is going to point down to n. So again, same idea, just more reference arrows to update. Same thing with removal. If we want to remove the 19, same example as before. First, we want to locate the element we want to remove. Then we just update the pointers. So I want to say curs next. So the 22's previous arrow should point to the 16. And I also want curs previous, which is 16's next, to point to the 22. And we can set cur to equal to null. And again, garbage collection. Now that there's nothing pointing to that node 19, it will take care of that node for us. Okay, so I'm going to talk about sentinel nodes next. Any questions about doubly linked lists? Okay, and so have you ever seen lists with this concept of a sentinel node before? No? Okay. No. Okay, so yeah, so I from what I saw in the 115 notes that I've had access to, I haven't seen them used. I'm not sure if 116 did them, but I think 116 usually aligns quite well with 115, so I don't think so. But yeah, so the textbook talks about this other variation. This is what we're going to do with our programming. And again, it's another way of thinking about our head and tail. So with sentinel nodes, again, they're just nodes that go at the beginning and end of the list, but they don't actually store a data value. So before, in the slides I just covered, our head and tail point to the last data elements in the list. But sentinel nodes, again, are going to be on either end of the list, kind of like, but they don't, yeah, so they're just keeping track of the beginning and the end, but they don't actually, they're not any, they don't hold a data value. So yeah, they're just markers. So again, when the list is empty, we've got these, yeah, we've got these two sentinels, head and tail, that point to each other, but they're kind of just, they don't actually have any values. Yeah, exactly. So instead of just nulls, it's empty nodes. And then when we put lists, we add list elements between them. So again, this list, we'd say this list has a size of 3. The first node in the list is 6, followed by 11, followed by 15. But we've got these head and tail nodes that are on each side. Yeah, they're just dummy nodes. I guess the benefits are that one, there's less checks for null, because every data element actually has a previous and a next. So so I guess there are certain ways you can do this that moderately can improve the implementation. And I guess the other argument is that it's maybe easier to use than having these nulls at either end. But this is, so again, why I'm showing you here is because this is how the textbook explores this new variation of a linked list implementation, specifically using this concept of a position, which I'll explain on the next slide. And then we'll jump into the coding for the last 20 minutes. So yeah, we can think of each node as having a position. And we can think of this linked list as a container of elements where each element is at a given position. And the positions are arranged in linear order. So there's the first one, and then the one after that, and after that, and after that, all the way to the end. So each position, when we've got these sentinel nodes, has something that comes after it and something that comes before it. So we can think of position as being something that we can define as something relative to its neighbors, where again, any given position has some position before and after. Whether or not that is a node actually storing a data value or not is something else. But it allows us to kind of come up with this definition where we can just think of the nodes as positions relative to each other. And using this concept of a position, we can define a linked list that has the following operations, where we can get the item, the element at the first position in our list, which again is not including the Sentinel node. So the first data element, the element at the last position in the list, the element before a given position, after a given position. Oh, that should be, sorry. We can insert before and insert after a given position in the list, and we can remove an item at a given position. And the idea here is that we're going to try and, by using this idea of a position, implement all these operations in constant time. So O of 1 time. And that's where, yeah, so I've given us enough time. I think we can now work through this Java example together, and that'll give us a chance to actually work on a Java program. So I know last Friday, I guess before last Friday, I posted the videos about Java programming, and some of you probably haven't programmed before. So what I'm going to do is take us through this Java code. So you should just be able to download all of these files, and maybe I'll just put them in what I have in here. I'll just put them in my documents, CSC 225. So the idea is that we're saving them all in the same directory is the first thing I want to show off. So now if I go to documents, I've got them all here, and I can just open them up in any editor. Again, we don't need to use, you're not required to use any special IDE for this course. But we've got these 4 different Java classes. So the first thing is an interface, and I think those of you in 115 are probably familiar with an interface, but those of you that took 116, again, I'm not sure how much you talked about them, but again, this is really just our specification document, which shows all the operations that we want to be able to implement. And I've added some documentation here just to say the purpose, the parameters, and what they all return. So again, for insert before, I'm saying we're going to insert, we're making a list of strings. We're inserting something before a given position, and we're going to return the thing we insert. So this whole idea is that we've got a position now, which the textbook really says is just another way of thinking about a node, where each of our positions has the data element and the positions that come before and after it in the list. And I guess the main thing here is that each position, the main operation a position have is it can actually get the piece of data that position stored at that position in the list. So yeah, the position class again just has the data, and it's got, I guess, kind of again references to the previous and next positions in the list, and we can get the data element. I've got some other methods that just allow us to change the previous and next. And then the position list is the only other one we're looking at this point, and it's just defining all the different operations we want to be able to do. So we can insert before and insert after, which are, I guess, probably fairly straightforward in terms of what how we'd expect that behavior to act. Again, getting the first gets us the first position in the list. So the first, again, position that has a data element. The last gets us the last element in the list that has a data element. And then we can get something before a given position, after a given position, and we can remove items at a given position. We're going to return the position, again, that node, that position that we ended up removing. Any questions about this so far? Okay, so now if I jump over to the linked list.java, again, if we're implementing an interface, what that means is that the minimum number of operations this implementation has to have are those defined in the interface. So it's kind of, we can, again, often interfaces are introduced as contracts, and the implementation of that is when you're fulfilling the contract. So you're providing an implementation for each of the operations specified in that contract, in that specification document. So if we're implementing an interface, and this is the notation to do this in Java, we're just going to have to have an implementation of all of the methods specified in the interface. And I think I've filled out the bottom four for you, the easiest for first, last, before, and after. And as again, so for first, we're actually saying we're just going to get the item after the head. For last, we're going to get the item before the previous. Before, we're gonna say as long as the one before this isn't head, we're going to return the item previous to this position P, and next is going to return the one after position P. So I guess now, if you remember implementing a linked list last, or in your prerequisite course, yeah, it may have been 2 years ago, so not necessarily last semester. Some of the issues with inserting before and inserting after, I guess the difficulties or the edge cases were when when it was the first or last element, and you had to deal with that null case because you couldn't. It was easy to get null pointer exceptions if you were trying to set. Again, if you were trying to say, let's insert it at the front of the list and let's go and set the previous nodes next to be this node, but the previous node was null, so you can't set its next. So that's a null that will get you like a segmentation fault or a null pointer exception or something like that, depending on the language you're working with. But in this case now, when we're inserting before a position, even if again, so these are kind of just bookkeeping nodes. They're not actually, they don't have data values. So even if we're inserting before this node, we still do have a node before it for which we can update its reference arrows. So we never have to worry about those null cases. So even, yeah, if we're inserting to the first data element in the list, we never have to worry about that null case. So in some ways, it really simplifies this insert before code, where what we want to do is, all we need to do is say that, okay, I want to make a new position or a new node again in my linked list. So I mean, we can call this whatever we want. I'll say position, new position equals new position with that string value. So what this is doing is this is saying, okay, I'm just making a new, I'm making a new node. So far, these are both pointing to null. But if I wanted to insert before, but it'll have, like, let's say I'm just going to insert an A. So I just made a new node with the right value, but I haven't actually put it, I haven't yet to put it into the list at the place I want to, I want it to be, I want to go into yet. So I've just made the new node. The next thing I want to do is I don't actually have to worry about things being null or anything like that. I can just go straight ahead and update the pointers as if I would in the middle of a regular linked list. So again, not having to worry about the null. So I can just say that I want this new positions next to be P. I can say the new positions prev is going to be the one previous to pre, which in this case, we see that this could but that's okay. That's fine. And then we just set, so P prevs next equals the new position. So again, in a regular linked list, this operation wouldn't work if we were inserting at the front of the list. Because in a regular list, if our head was pointing to the first data element and we tried to say, go to its previous, which was null, and set its next to be equal to the new node, that would get us, that's where our program would crash. But with this new implementation, even if we're inserting before the first item here, it does have a previous. It's got that sentinel node as its previous. Does that make sense? So this is one of the nice things about using these sentinel nodes. And then the last thing we have to do, so what we've done right now, we've said, okay, let's make, I'll just draw this with our thing right here. So we've made this new node, we've set its next previous. We just need to set the last thing here. I'll do it in a different color. Is we want to set. Oh, the last thing we want to do is set P's previous to point to that new node and erase this last pointer. So the last thing we have to do here is just say P's previous is set to the new node we just created, and then we're returning this new node or this new position. Sorry. So it's these same things. All we have to think about with this implementation is just updating these 4 pointers. And it works if we're at the front, at the back, no matter what, because every node is going to have a prev and a next. So really, there's just no edge cases, which makes, again, the implementation arguably a little bit easier to work with. Does this make sense? How, again, we've changed it, so we've now got these bookkeeping nodes as opposed to the head and tail pointing to the last one. So I'll jump over to our linked list tester now. Or let me, what's going on here? Okay. So our list tester now, again, in Java, we're always going to immediately run the main method. And I've just made a new linked list and I've said, I'm starting at the head, and then our first 3 operations here, I'm just saying, let's insert after head, then let's and get that position. Let's insert after that first position, then insert after that second position. So I'm just calling the insert after. Is that what we did? Did we do insert after before? Oh, we did insert before. Let's do insert after too. So insert after is going to be the exact opposite. We're going to make a new position. And again, if we want to insert after something, we know that the new node's previous is going to be the position that we're inserting after. We know the new node's next is going to be the old position that we're inserting after is next. And then we can say that the position we're inserting after's next prev is now that new node. And the node we're inserting after's next is now going to be the new node we created. And then again, we can just return that new node again. So again, the same idea. Again, we're just thinking about the 4 different reference errors we need to update. And so again, we're always updating but we need to be a little careful about the order we make these updates. 10, 11. Okay. So again, I'll save this and hopefully I was careful with my order. But now again, if I go to the tester, I can try some insert afters. And again, so now I know maybe some of you haven't done command line stuff before. So again, now the two steps for running a Java program are, first we're going to compile it. And here, if there was a compile error like here, it should tell me that, again, on list_tester.java, on line 14, there's an error somewhere there. And sometimes it doesn't get you in the right location. This thing, it did say that there's an error right at the end, which is nice. Sometimes, again, it won't be as accurate, but again, it usually gives you the right line number and definitely the right file that the error occurred. So again, if we compile and there is no compile errors, nothing will show up here. And then we can run the program by typing Java and then the program we want to run. And we see that, again, what we created here is we started with just a head and a tail that pointed to each other. But then we said, let's insert after the head something with data value f. So what that did is that said, okay, we know that we're going to update the 4 pointers. We're saying, let's make this pointer go to next pointer. This one's prev go to the next. And then we said, let's go to the previous next and make its back arrow come here, and then make the previous's next go to that new node. So we're kind of doing it in, that's the order that we did it in our insert after. And then again, we just inserted a U after the F. So the next thing we did, so that we just completed that first line, then we inserted a U after the F. So we said, let's now insert a U here. Let's make its next go to F's next, its previous go to F, and then let's make F's next previous point here and F's next point here. So again, we can see here how we got this order. And then the last one we did with the same idea was we made a final node with N to go here. So a couple of things to note here. One thing is our insertion methods are returning the node we're inserting. So, and why that's a big deal is because that allows us to always give it a position to insert before or after. So yeah, that's a key thing is here that we see that we're always getting a position back from our insertions. And that allows us to not have to traverse to a given position like an index-based number to insert these things. We're never saying, I want to insert this 3 places from the front. We're just saying, I've got this object, I want to insert it before or after this object. If you didn't insert before, it would be, but I guess, yeah, the textbook conveniently always starts with a list that already has elements in it. I guess the idea here is that you would, I think, generally in your implementation, these would be private, and you'd probably would never actually be able to even access head or tail. So I kind of worked around that here just by having a method that got me the head. But yeah, the textbook when they're talking about this example conveniently just always works with an example. And they say that you can remove from the front of the back, but you're kind of just assuming that these bookkeeping nodes are already there, and you can't really work with them directly. Yeah, exactly. So again, the I can print things before and after, which is just, I'm giving it one of the nodes, and I can easily just say, hey, what's the node before or after that? So I can say what's after the first node, or what is the first node? It's an F. What's after the first node? It's a U, and what's the last node? It's an N. What I want to do now is, and this isn't going to quite work, is I want to now test my insert before, which we get this, but I also want to remove the item at the first position, this F, so we go from fun to noun. So the last thing we'll do is try and really quickly do our remove. Where did I put remove? Oh, there it is. And again, we never have to worry about when we're updating our pointers about there being a null pointer. So with our remove, again, even if we're removing again, this has only really got 2 elements in it, 7 and 3. Even if we remove the first item, we can still, it still has a previous for which we can set its next pointer to go past it. So even if we're removing the first item, it still has a previous, which is our sentinel head. So we still can actually set its previous next, which in a regular, again, in a regular linked list, we wouldn't be able to do this. So this remove becomes really, really simple. Again, all we have to do is say p.prev.next equals p.next, and p.next.prev equals p.prev. And then they can just return p. So again, no matter where this is in the list, we know that it has a prev, and therefore we know that we can actually set its prev and its next. It can update their pointers, because at the worst case, those are just the head and the tail sentinel nodes, but those still exist, and they still do have next and prev pointers. No, well, we are returning the element we're removing, kind of, I guess, similar to like a pop or a DQ. So it's no longer going to be, that object is no longer, we've, I guess, set the arrows here. So if we remove 7, we change it so our head now points to the 3 and our 3 points back there. So there's, in our, as far as our node, our list is concerned, the 7 isn't part of our linked list, but we still do return this object because we might want to do something with it as we remove it. So it's no longer part of the linked list, but we still, wherever we removed it from, we still can print out the data or do something else with it. Does that make sense? So I guess I can save, oh, I can stop drawing, I can save hopefully, and we can try running this one more time. So now we've added before and after things, and we have removed an item. So we've gone from fun to noun. Yeah, yeah. So I guess the last thing I want to do, the textbook doesn't really talk about this, but I do think it's worth talking about. So they, in summary, say that we can show that the running times of these position-based methods are all constant time, which looks great. And it looks like this is definitely a better implementation than our array-based implementation. But again, I think it's important to remember that accessing an element n spots from the beginning or n spots from the end is still going to require a traversal. So this works if we have the object we want to insert before or after, because then we can access that and update the arrows from that given position. But sometimes, and maybe in the program we're working with, we always do have references to the objects that we want to insert before or after. But sometimes we might just say, oh, I want to just find the 10th element in the list. This would still require traversal if you didn't know exactly, if you didn't have that object, access to that object directly. There, one second, I'm just trying to read that. There, yeah, so Scott, what I'm saying is that a user of this would never have access to header tail. They wouldn't even know that they exist. As far as like a size would print out, it would, if you've got one element, it would print out one. It wouldn't print out the three, including the head and tail. So I guess from a client or an end user perspective, they don't know that this implementation has these sentinel nodes, just like you might not actually know that this list was implemented with a linked list or an array. So I guess technically someone should never be able to insert before or after a header tail because they shouldn't even know that they exist. Yeah. Yeah, so what I wanted to say was the array implementation is still more efficient for getting a value at a specific index or placing a value at a certain index. But obviously if you say, okay, I know I've got this element which is somewhere in my list, I want to insert something after it. Obviously, this works better because in an array, you're going to have to do some shuffling to insert something at an index in the array after or before a given index. I guess unless it's after the very last index. The position is, I guess, just an abstraction of a node. It's just another way of thinking about a node, but really you're just thinking about it as I've got these elements and I can think about them as being relative in my list, I guess positioned relative to other elements. So the last thing I want to say is, again, what I think the takeaway is from this kind of quick refresher review unit is it's important to think about how we're going to use our program. So again, if we've got a list and we know that we're often going to be saying, okay, I want to insert or remove things before or after these other objects. And it's always going to be relative to other objects, or you know they're always inserting from the front or the back, but not necessarily n indexes into the list, then a linked list is a great choice because it doesn't require the shuffling of all these elements. Whereas if you know that maybe you're not going to be doing a lot of insertion or removal from this list into the middle, it's more just that you've got a lot of operations where you're going to be accessing things in a different position, then obviously, or at a certain index, then obviously an array implementation would be better. And yeah, I will talk about that in a second, Andy. But yeah, that's kind of the main thing I want to get out of this, I guess this review chapter is just when we're developing, I guess programs at this point, if we know how they're going to be used most commonly, that might help us in our implementation decisions. So I'll ask one more time for questions. I can wrap it up here because I know people have labs and whatnot, and then I'll jump to any last. Then I can jump to your question, Andy. Okay, I'll call it here for the recording then.
The recording has stopped.